Hey everybody. I hope you guys are all doing well. Today we're going to do a quick discussion on solubility and in light of what will be on the exam, special exam this year. So we're going to cover the section 16.1 and we're going to talk a little bit more than just 16.1, but it's generally within there. So this chapter 16 is about solubility, so substances that dissolve or somewhat dissolve or hardly dissolve at all. So generally speaking, this first paragraph here just tells you that when we talk about a substance that's soluble, like sodium chloride, what we're saying is that it dissolves more than 3 grams per 100 milliliter, which is a fair amount. But anything that is less than 3 grams per 100 milliliter, that's what the Ksp, what we're going to talk about today, that's in that realm there. So the Ksp stands for solubility product constant, yet again another K. But the nice thing about this is that it's going to help us review as well precipitation reaction and net ionic equation. So speaking of, we have a diagram here, and what this is showing is a precipitation reaction. So when we're forming a precipitate, right? So that's like a double replacement reaction, but one of the product is not soluble or slightly soluble. So what's going to happen is that product is what we refer to as the precipitate. Here, the reactants are silver nitrate, which is soluble because you remember the solubility rules. Anything with nitrate, anything with NO3 is always soluble. So this, always soluble. The other substance is NaCl, and also from the solubility rules, any alkali metal. Right. Anything in the first column of the periodic table is always soluble. So we know that NaCl will be soluble. So therefore, in the products, Na plus and NO3 minus as aqueous ions. What is not soluble, or slightly soluble, is the silver chloride. So this, with the little solid sign, this is our precipitate. So that's the solid that we get. So when you write the net ionic equation, you don't write the spectator ions, which means that anything that is aqueous gets taken out, right? Because the AgNO3 at the beginning, that was Ag plus and NO3 minus. Likewise, NaCl at the beginning was Na plus and Cl minus. So we see that the Na plus remains Na plus, NO3 minus remains NO3 minus. So those are the spectators. So spectator ions. And those guys are out of the net ionic equation. So what you're left with is just what reacts, essentially, what precipitates. So the silver ion, the chloride ion, and the silver chloride precipitate. The solubility equation. So when they ask you to write a solubility equation, it's the reverse process because it's as it is being soluble, so as it dissolves. So the solubility equation always starts with the solid and it goes into the ions. So the solubility equation, it's the solid that dissolves. So here we said, well, okay, so maybe you're thinking, wait a minute, we just said that it didn't dissolve, right? And this is what this chapter is about. When we say things don't dissolve, we don't really mean don't dissolve at all, right? Going back to the 3 grams per 100 milliliter, what we're saying is it dissolves less than that. So there's a certain amount that dissolves, even though we say it's a precipitate and it's not soluble. So keep that in mind, right? So not soluble, it's just in reference to a 3 gram per 100 milliliter. So what happens is, in fact, this AgCl, silver chloride, the precipitate, a small fraction of it is going to dissolve. And so there will be a very small concentration of Ag plus ions, and there will be a very small concentration of Cl minus ion. And this is what this chapter is about. It's about measuring this concentration. How much is there? Of course, those numbers are pretty much always going to be very, very small. So if you take this equation right here, okay, so the dissolution equation, and if it's an equilibrium, so we could write the K value for this equilibrium. But because it's a solubility, it's kind of like when we did acids and bases, the equilibrium constant K, we called Ka for acids or Kb for base. Because this is a dissolution equation, we call it the solubility product, right? It's the product of this dissolve as the substance dissolves. And that's the SP. So solubility product. So it's the K value, like all the other Ks, products, concentration of the products over concentration of the reactants. But in this case, the reactant is a solid. And you recall, solids and liquids do not go into the K equation, right? So therefore, the Ksp equation is only Ag plus and Cl minus. That's it. So when they asked you to write a Ksp equation, we're going to do a couple of those. This is all that we're going to do. Now, sometimes this, when you balance this equation, you get a 1 and a 1. Sometimes you don't. Sometimes it's CaF2, so calcium fluoride, that's dissolving. So you're going to get the calcium ion, but calcium is a 2+ ion, and the sulfide is a 1-. So there's 2 of those. So when you write your dissolution equation, so be mindful of that over here. Because what's going to happen now is that when you write the Ksp for this equation, you're going to write concentration of Ca2+, but now there's 2 F-, right? So it's going to be F-, F-, which means that it's going to be Ca2+ and F- squared. So when there's a 2 in the balanced equation, it becomes squared. And if there was a 3, then it would, be fluoride, 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 so it would be cubed. So this is what's happening over here. Again, we talked about the solubility process before. Water is a polar substance, right? And so we did the dipole moment, which made this end of the molecule slightly negative, this end of the molecule slightly positive. And because water is so polar, what it does is it attracts, say, this negative ion, right, is attracted to the positive side of the water molecule, and this little, and this positive ion over here would be attracted. So the little red guy, positive, right? It would be attracted to the negative end of the water molecule. So what's happening is a salt, the crystal, is being picked apart by the water, right? The water is like grabbing little pieces of the crystal, and so it's shrinking and shrinking and shrinking, and eventually it dissolves. This is what we see when something dissolves. So, but at the same time, what's going to happen is this is an equilibrium system. So there's some ions that break free from the crystal, and there's other ions that will rejoin the crystal. And that's why it's at equilibrium. So then there's tables that give you Ksp values. And the question that they often ask is, oh, well, look at these substances and look at their Ksp, and for sure, this is more soluble than that because its Ksp is larger, right? The larger the Ksp, remember that the Ksp is the product of the ions in solution. So if the Ksp gets higher, that means that there's more ions, which means it's more soluble. So when the Ksp increases, the solubility increases. But here's the thing though, you have to be careful. You have to compare substances that have the same number of ions. Because otherwise you're going to get some ions that are squared and others that are not, and that's not going to be a fair comparison, right? So what happens over here, for example, if you look at barium fluoride, well, this is going to give you 3 ions. So it's the concentration of barium 2+ times the concentration of fluoride minus squared. Well, you can't compare that directly with this because barium sulfate, that only gives you 2 ions. You get the barium 2+, and you get the sulfate 2-. So that number is just the product of 2 ions, not 3. So be very careful. You can only compare the solubility of substances by looking at their Ksp if they have the same number of ions. So when we write the Ksp expression, again, very simple, products over reactants like we've learned all year, but because the reactants are solid, they're simply not included. So the Ksp is the concentration of Ag², and there's 2 of them, so it's squared, and then times the concentration of CrO4 2-. And this is not squared because there's only 1 of those, right? That's it. So here is a concentration of calcium 2+ times the oxalate ion, and that's it. So as far as solubility, again, this is a calculation that normally we would do. However, this year on the test, they said that you're not gonna, or the use of the calculator is minimal. So you're probably not gonna have to calculate something like this, but you would have copper 1 bromide. So this would be CuBr, because copper 1 means Cu1+, right? And bromide is 1-. So this is a solid, and it's going to be at equilibrium, you're going to get Cu1+ plus Br1-. So the Ksp is equal to Cu plus times Br-. The solubility, that means that this is the amount that dissolves. 2 × 10⁻⁴ moles per liter. So that means that you're going to get, if your CuBr is 2 × 10⁻⁴ molar that dissolves, you're going to get 1 and 1. So this is going to be 2 × 10⁻⁴, and this is also going to be 2 × 10⁻⁴. And that's your Ksp value. It's super simple. We're going to skip this problem. I would like to talk to you about common ion effect. And the reason for that is because this touches on Le Chatelier's principle and the equilibrium, and so they may bring this up. So you can calculate the solubility of the solid CaF2, but this is in an NaF solution, right? So what's happening is your calcium fluoride, CaF2 solid would dissolve and give you Ca2 plus 2F minus, right? But look at this. This is not in water. This is in NaF. So you're not putting this calcium fluoride, you're not putting it in water, in pure water. You're putting it in water that already contains some Na plus and some F minus. So the question might be, how does that affect the solubility? Well, you know how it affects the solubility because we've talked about Le Chatelier's principle, right? And what's happening here is that this contains some F minus ions. There's fluoride already in there. So what it does is it increases the concentration of the fluoride, which means that the equilibrium will shift to the left, which means that the CaF2 would be less soluble than if it wasn't pure water, right? And so this is called a common ion effect. So what you're trying to dissolve has an ion that's in common with what's already there. And so that's going to lower the solubility. It's going to push your equilibrium to the left, where the substance is a solid. On the other hand, if you had a substance that would lower the concentration of an ion in solution because it would, say, react with it to form a precipitate, right, then it would increase the concentration. Like, for example, if this had been in a solution of sodium sulfide, then what would happen is this calcium would actually precipitate with the sulfide that's in the solution. So what that would do is it would lower the concentration of Ca2+, which would shift the equilibrium to the right. So if the solution had been NaS, that would increase the solubility. So I hope this all makes sense. I think what we need to focus on here is writing a dissolution equation. You absolutely need to be able to write a net ionic equation, Ksp value, and remember shifting the equilibrium using Le Chatelier's principle. And with that, I wish you a nice week and study hard. Thank you.